Okay, good evening. Today, this is Sudhir, and today I would like to explain my thesis title is an intelligent hybrid monitoring framework for efficient classification and aging analysis of heat shrinkable polymeric materials under the supervision of Veeran sir. And one second. And let me justify my contents. Today I would like to explain abstract, introduction, literature survey, and followed by the motivation and objectives of the research and the proposed approaches, experimental results, conclusion, and followed by the future work and references. Coming to abstract, so my research introduces an intelligent hybrid machine learning framework. Why I have chosen machine learning is emerging under artificial intelligence, and it is very famous algorithm techniques which integrates three popular techniques for my research. I am going to classify the given input data by using random forest, gradient boosting, and support vector machine models to classify and analyze the aging behavior of heat shrinkable uh, polymeric materials under multi-stress conditions. So various conditions we are applying for that materials, then we are classifying the data. The proposed system demonstrates, so in order to avoid the existing drawbacks of existing system, we are using proposed system. It demonstrates exceptional predictive accuracy, we got it, and reliability, effectively linking key degradation parameters with the polymer aging for improved quality assurance and predictive maintenance applications. These are my keywords for my research: hybrid machine learning and polymer aging analysis, heat shrinkable materials, random forest, gradient boosting, ensemble classification, thermal degradation modeling, predictive maintenance, etc. Coming to introduction, heat shrinkable materials are polymeric insulators widely used in power distribution systems, and aging leads to degradation in mechanical, dielectric, and electrical properties. And based on my in this research, I would like to use polymeric materials as input to the system, and these are the objectives I am using: develop an AI driven model to classify aging stages and predict degradation accurately, and focus materials like a cross-linked polythene, uh, polyethylene XLPE, and polyolefin blends. So these are the two things I am concentrating. So these are the examples of shrinkable materials like silicon rubber, SIR composite insulator, EPDM, ethylene propylene dine monomer insulator, polyethylene PE insulator, cross-linked polyethylene, that is XLPE insulator, and polyvinyl chloride PVC insulator, polytetrafluoroethylene PTFE Teflon insulator, polycarbonate PC insulator, and polypropylene PP insulator, and polyimide, that is PI insulator, and a hybrid nano composite polymeric insulator. These are the examples of shrinkable materials. I am concentrating on cross-linked polyethylene XLPE insulator. So this is the uh, introduction diagram for a hybrid machine learning framework for a polymer aging analysis. Heat shrinkable polymeric materials we are using as input material, and heat shrinkable polymeric materials we are giving to the cloud environment called a hybrid machine learning algorithm, which combination of random forest, gradient boosting, support vector machine, and a stacked meta classifier, and finally we are getting classification. If we are not getting above 90% classification, We are again improving size of the data and number of iterations we are performing, so that how various models collaboratively classify and analyze the aging behavior of heat shrinkable polymeric materials. We are enhancing predictive accuracy and performance. Then this is the research motivation. Existing models lack robustness and interpretability. Manual assessment of aging properties is time consuming and inconsistent. There is a need for an automated data driven system integrating hybrid ML models to evaluate polymer degradation efficiently. And this is the literature review. I have collected 75 literature survey papers so far for my research. Out of 75, I kept only 10 which are closely related to my research, and these are the 10 columns I have taken as prime parameters for considering literature review based on my 75 research literature survey papers. The first column is author name and his team. ETAL means including remaining authors. And I have identified limitations or issues or challenges for my research. Existing method what they have used in their research, and the proposed system they have used in their research paper in order to avoid the existing drawbacks. Then what's next, data set utilized, then techniques applied. What are the latest techniques with incorporation of AI, machine and deep learning techniques? And what are the tools they have used in these 10 papers I have mentioned? Then validation metrics what they have used for justifying our model is correct or not. Future directions. Um, in that papers I have identified research gaps I have taken into account, and from this reference and digital object identifier or uniform resource locator I am downloading the papers. So the first author Hamadi and his team, they have done a wonderful research in this research paper. They have identified limitations, issues, challenges like optimization challenges in hardness, prediction of alloys, existing method like a conventional heat treatment models, then proposed approach like fuzzy logic plus simulated and healing hybrid methods they have used. And this paper is published in 2024, and their data set they have used experimental 2024 aluminum alloy data set they have used. Then techniques applied, fuzzy modeling, simulated and healing. Tools they have used MATLAB. Validation metrics they have used RMSE and MAE. The based on this one we can check the accuracy classification. Okay, accuracy of classification. Then future direction we are using integrating deep learning with fuzzy modeling. We are using our research paper. This is a survey, and from this URL we are downloading. Like this, remaining 10 papers of literature review. Coming to the first closely related to my research topic, I have taken as a base paper. Priya Selvamani and his team they have published in this paper in the year 2022, and the title of the paper is Investigation of XLPE cable insulation using electrical, thermal and mechanical properties and aging level adapting machine learning techniques. Um, in this paper, they applied supervised machine learning techniques. Why it is a supervised learning means there is a label, there is a target class. Based on the label and the target class, we are classifying the data. Um, and in this supervised learning methods, we are using various machine learning techniques such as regression and classification models to analyze the electrical, thermal and mechanical aging behavior of XLPE cable insulation, enabling accurate prediction of material degradation levels. So drawbacks like I have identified from the literature review. limited data set representation, lack of multimodal feature integration, absence of hybrid or ensemble modeling, restricted validation and generalization analysis. Then so myself I have published one research paper in the year 2022, an efficient analysis scheme for a classification of heat shrinkable material based on aging with the aid of learning techniques. So this paper, one contribution chapter I have implemented based on this one, and the techniques I have employed machine learning based classification and aging prediction techniques that integrate supervised learning models to analyze performance degradation patterns in heat shrinkable polymeric materials. And the drawbacks in this paper: limited data set diversity, lack of hybrid or ensemble integration, absence of cross data set validation, insufficient explainability and performance metrics. Then, according to Lee and his team, the paper is published in the year 2024. The research paper title is Machine Learning Models for Polymer Degradation, a comprehensive review. In this paper, they have used review paper and compares various machine learning and hybrid modeling techniques, including neural networks, ensemble learning and physics informed models for predicting polymer degradation lifetime estimation and aging behavior under varying environmental and thermal conditions. In this paper, the drawbacks like limited experimental validation of models, insufficient focus on hybrid deep learning integration, lack of standardized data sets for polymer aging analysis, minimal discussion on real time industrial implementation. So, to avoid these drawbacks, we are going to use a proposed model. That proposed model is a hybrid machine learning framework for classifying heat shrinkable polymeric materials. It takes as input system heat shrinkable polymeric materials, and we are giving to hybrid machine learning, random forest support vector machine gradient boosting. With the combination we can call it as a hybrid machine learning. Then finally we are getting classification with a very good accuracy. These are the research objectives so far I have identified: analyze parameters and affecting polymer aging, evaluate physical, mechanical, dielectric and electrical properties, develop develop a hybrid machine learning framework with inclusion of random forest, gradient boosting and support vector machine, classify polymers into 5 aging categories, validate with metrics like accuracy, F1 score, ROC, AUC, log loss and time complexity, etc. And in the existing system, based on my 75 papers literature review, I have compiled the traditional machine learning models such as artificial neural networks and fuzzy logic based methods for classifying and predicting the aging properties of heat shrinkable polymeric materials, which often face limitations in accuracy, generalization and computational efficiency. And from 75 paper literature review, I have taken 6 major drawbacks and common drawbacks from all 75 papers, and these drawbacks I am avoiding in my proposed system. Drawbacks like limited data set diversity and generalization, inadequate integration of hybrid and ensemble models, insufficient correlation between thermal, mechanical and dielectric parameters, poor interpretability and explainability of prediction models, high computational cost and risk of model overfitting, lack of real-time validation and industrial application testing. In order to avoid these drawbacks, I am proposing a proposed system is a intelligent hybrid machine learning framework. Keep in mind, what is your proposed system? My proposed system is a intelligent hybrid machine learning framework which integrates random forest, gradient boosting, support vector machine and a stacked meta classifier to accurately classify and predict the aging behavior of heat shrinkable polymeric materials by correlating their thermal, mechanical, and dielectric degradation parameters for enhanced reliability and lifespan forecasting. By using this hybrid intelligent machine learning framework gives advantages like high predictive accuracy, robust multi-parameter integration, improved generalization, reduced log loss and better calibration, enhanced interpretability and correlation, support for industrial application. So this is a flowchart for my proposed research work. Parameters and data set I am taking as input, and base learners like random forest, gradient boosting, support vector mission. These are the traditional and supervised machine learning algorithms in the case of classification. Finally, it combined as a stacked meta classifier. So in this one, multiple base learners we are using, and we are designing to accurately predict the aging behavior of heat shrinkable polymeric materials using key degradation parameters. So methodology I am using: first step, data collection, which includes thermal, mechanical, dielectric parameters, and second step is a pre-processing. We are eliminating normalization, feature selection, stratified sampling, model training, random forest, gradient boosting, support vector machine, hybrid ensemble meta classifier integration, and we are validation and comparison of existing models with the proposed system. And the tools I am using a Python, which includes libraries like scikit-learn, sklearn, pandas, matplotlib, Jupyter, TensorFlow. So proposed framework architecture, we are taking as input polymer dataset, that is thermal aging tensile strength and dielectric loss oxidation index. We are extracting feature extraction from their hybrid model integration and classification and visualization. Multimodal fusion ensures generalization and interpretability. So this is the input data set I have taken from GitHub and Kaggle repositories, freely available data set, sample ID, polymer name, chemical structure, density, tensile strength, and elongation at break, then crystallinity, glass transition, temperature, melting point, dielectric strength, thermal aging time, thermal aging temperature, oxidation index, color change index, surface roughness, shrinkable ratio, shrink ratio, electrical resistivity, and mechanical degradation, data set source, target class, source ID. Finally, we are classifying whether the material is fresh or aged or mild, and aged moderate, and aged severity severe. Like we are classifying the materials. That is our target class. So this is the proposed hybrid machine learning framework for polymer aging analysis. Data set we are taking from Kaggle and GitHub, and we are supplying data set as input to the data lake. From there we are pre-processing, means we are eliminating noisy data like cleaning, normalization, imputation, outlier scaling. Model selection and calibration we are performing, which combination random forest, support vector mission, etc. Then explainability, where we are using sharp method, feature, ROC, AUC, log loss. These are the validation metrics. And we are applying applications like active learning, drift monitoring, which is called multi-class outputs like fresh, mild, moderate, severity, critical. So that is a final class. Before that we are deploying. Explainability says that various validation metrics like accuracy, F1 score, ROC, AUC, log loss, confusion. Then we are using active learning, feature engineering, their stacking of log regression, This is a model. From that feature engineering we are giving as input to the system. Then experimental setup, I have used data sets from Kaggle, like polymer data set, extended polymer data set, polymer aging input data set. So custom experimental data sets. Training purpose we have used 80%. Training purpose 20%. Testing 20% for testing, 80% for training. Validation like k-fold cross validation we are using. Models tested with random forest, gradient boosting, support vector machine, artificial neural networks, hybrid stack. These are the five techniques we have tested. This is the flow chart. Start and data collection, polymer materials, feature extraction like we are using random forest, gradient boosting, support vector mission. These are the supervised machine learning techniques. We are performing classification and output we are getting flowchart for the proposed system and end of the statement. Then steps of proposed algorithm. First step we are collecting data collection. Then we are performing data pre-processing, means eliminating noisy data, inconsistent data, dirty data, feature selection. So here identify key degradation features influencing aging through statistical correlation and expert analysis, model initialization, configure three base models like random forest, gradient boosting, support vector machine. Then model training, for training 20%, 80% for training, 20% per testing we are using. Hybrid ensemble integration means combining outputs of all base learners using a meta classifier, that is called stacking approach. Model validation by using apply k-fold cross validation to evaluate model stability and generalization, and performance evaluation like accuracy, compute accuracy, FN score, ROC, receiver object characteristics, area under curve, and log loss for comparative analysis. Results interpretation finally, with help of analyze confusion matrix, ROC curves, and feature importance for explainability. Final prediction and deployment, classify polymer samples into aging categories and generate insights for predictive maintenance. And model performance, I have applied three models with parameters like accuracy, FN score, AUC, log loss time. So random forest shows the best performer model. We got 100% of accuracy. Next one, gradient boosting, I got a 98.9. Support vector mission I got 97.5. That only you have to tell. Then experimental results in the x-axis. After implementation of successful my research with polymer materials as input to the system, I have choose the intelligent hybrid model for proposed system. So in x-axis boosting iterations like number of iterations. In y-axis we are taking validation accuracy. Then we are using validation log loss curve for gradient boosting model. Like uh, in x-axis we are taking boosting iteration, number of epochs, validation log loss we are calculating. Then ROC curve for random forest model, I am justifying my model is correct, that hybrid model. X-axis I am taking false positive rate, y-axis I am taking true positive rate. Based on that we can explain the accuracy of the proposed model. This is the confusion matrix. You can take it as in this confusion matrix based on the number of samples correctly classified by using a hybrid model for random forest model, showing perfect alignment between predicted and actual aging classes with no misclassification. Then time complexity comparison models we are using. hybrid stack, support vector machine, gradient boosting, random forest. So we got training hybrid stack took too much time. Predicted time is in y-axis. Okay. So random forest shows the best classification model. Finally, I am comparing my analysis parameters, existing system, proposed system. So my parameters like validation accuracy, random forest shows the proposed system 100%. Fn score and followed by the ROC AUC macro, log loss, training time, inference time, etc. Then we are comparing the same thing in existing system and proposed system. Validation accuracy we got 80 to 90, and here I got 100% accuracy. Then macro F1 score like ROC, AUC, log loss, training time, prediction time, interpretability and explainability, scalability and industrial integration. We are using on this existing and proposed system. We got very good results. Then key, you can call it as key things like random forest achieved a preferred perfect classification across all polymerizing stages. Gradient boosting demonstrated fast convergence and minimal log loss. Ensemble models enhanced stability and predictive precision. And thermal, dielectric, and mechanical indicators show strong correlation with aging progression. And discussion about my proposed framework which handles the multi-parameter non-linear degradation patterns effectively. It offers superior interpretability for predictive maintenance. It can be extended for other polymer families and industries diagnostics. So this is my conclusion about hybrid machine learning framework provides a reliable and efficient aging prediction system, enables automated material classification, reducing manual inspection cost. It contributes to sustainability and long-term reliability of polymer-based insulation system. This is my future work, and I am going to submit two site Scopus papers in near future based on my thesis. Integration with the federated learning for distributed lab collaboration. Incorporate deep generative models like generative adversarial networks GAN and autoencoders for synthetic data expansion, deploy in real-time predictive maintenance and platforms in industrial settings. And finally, I have used 75 references for my proposed work, and a few references I have incorporated here, 15 papers, and followed by the free repositories where I have downloaded. Then list of publications. So far I have published two papers and two international conferences, and thank you for giving me this wonderful opportunity. So with this one